The universe operates upon a foundation of rules. We rely on physical laws to predict celestial behavior, planetary orbits, stellar evolution, cometary trajectories. These patterns form the framework for our cosmic understanding, yet sometimes unexplained anomalies arise. These anomalies compel us to re-examine everything known today. We explore precisely such a case. An interstellar visitor intruding into our solar system. Its behavior challenges our most fundamental astronomical models. This object, dubbed Three-Eyed Atlas, originates from distant interstellar space, its origins and purpose unknown. During its most recent approach to our Sun, a perplexing event occurred. After reaching its closest point to the Sun, the so-called perihelion in orbital mechanics, its velocity underwent an anomalous change. According to our established gravitational theories, an object's velocity after flying past the Sun should precisely follow gravitational model predictions. This model accounts for the Sun's gravitational dominance and minor planetary perturbations. Yet Three-Eyed Atlas defied this rule. Its measured velocity significantly exceeded predictions. This discrepancy was not a minor observational error, but a substantial, undeniable deviation. This deviation signifies a fundamental problem. Either our understanding of natural forces contains a major flaw, or an unknown force is at work, one that may transcend existing physics. It might not even be natural in origin. The implications of this discovery are profound. It concerns not merely one interstellar object, but our very understanding of how the entire universe operates. If natural laws are being violated here, we must uncover why. If this violation stems from intelligent intervention, human civilization faces unprecedented circumstances. I invite you to join me in unraveling this mystery. Wherever you are in the world watching this video, you become part of this journey of exploration. This channel is dedicated to revealing the mysteries of space, and today's content may surpass all previous revelations. We will examine publicly available scientific data, conduct rigorous logical reasoning, and explore every possibility, from the most conservative natural explanations to the boldest hypotheses. Our journey begins with this anomalous event, gradually delving into its profound implications. Next, you will see precise measurement data and understand why this acceleration is so extraordinary. We'll also examine the natural explanations proposed by astronomers and analyze why these explanations fall short of convincing. Ultimately, we'll confront the unavoidable question: are we observing a technologically advanced object? Are we witnessing the product of an extraterrestrial civilization? Remember, the core of science lies in questioning and verification. We won't jump to conclusions, but we have the courage to follow the evidence wherever it leads. Now let's begin this journey. First, understand this anomaly that defies the model. To comprehend a scientific anomaly, one must first examine its data. The Three-Eyed Atlas is not a vague speck of light. It is an object precisely tracked by a global network. Its orbital data is continuously updated by the International Astronomical Union. Our analysis is based on these publicly available, authoritative measurements. The object reached its perihelion on October 3rd this year. At this point, it was 0.7 astronomical units from the Sun. This position lies just inside Mercury's orbit, within the Sun's strongest gravitational field. Using Newton's laws and Kepler's equations, we can precisely calculate its expected velocity. This calculation accounts for the Sun's dominant gravitational pull and fine-tunes for the minor perturbations of inner planets. The orbital dynamics model predicts a speed of 46.2 kilometers per second. This is a peer-reviewed, reliable value. However, global deep space monitoring networks, including radar data from Goldstone and Goldstone stations, yielded a starkly different result. Actual measured velocity exceeded predictions by 300 meters per second. Note, this is not a momentary velocity fluctuation, but a sustained, cumulative, steady increment. Over a 30-hour time window, the object's velocity systematically deviated from the theoretical curve. The figure of 300 meters per second requires contextual understanding. At atmospheric speeds, this falls just below the speed of sound, and may not seem remarkable, but in the realm of orbital mechanics, it represents immense energy. We call this delta V, or velocity increment, a core metric for measuring a spacecraft's maneuverability. To grasp the significance of this value, consider a simple analogy. Given the massive mass of the Three-Eyed Atlas, the kinetic energy contained in this acceleration equals the full thrust of a large chemical rocket. Energy release of this magnitude cannot stem from chance or minor natural events. It fundamentally alters an object's escape trajectory. Comparing orbital data before and after perihelion reveals a path deviation from initial predictions. This deviation carries profound dynamical implications. A simple analogy: a slight turn of the steering wheel on a highway is enough to exit at one ramp instead of continuing toward your original destination. Trigon Atlas underwent precisely such an orbital shift. This acceleration brought its flight path closer to Mars. Initial calculations indicated its closest approach to Mars would be 280,000 kilometers. The revised orbit reduced this distance to 160,000 kilometers. This means it will enter Mars's Hill sphere even closer than Phobos's orbit. This trajectory adjustment is remarkably precise, as if meticulously calculated. We must also examine the timing of the acceleration. It did not occur randomly at any point during the flight, but was tightly concentrated near perihelion, where the sun's gravitational influence is strongest and the object gained additional thrust. From an engineering perspective, this is the most efficient timing. Applying thrust where gravitational potential energy is greatest achieves maximum orbital alteration with minimal fuel expenditure. This aligns with every orbital optimization strategy we know. Whether for artificial satellites or interplanetary probes, all adhere to this fundamental principle. Therefore, this anomalous acceleration event is not merely a deviation in velocity figures. It is a complete phenomenon encompassing magnitude, direction, timing, and the consequences of orbital alteration. All these characteristics collectively point to one conclusion: what we observe is a highly non-random, potentially controlled physical process. Having ruled out all known natural mechanisms, we must begin considering those explanations not yet incorporated into conventional models. In the next section, we will delve into these natural explanations and examine why they struggle to hold up against the data. When confronted with unexplained observations, scientists' primary task is to seek all possible natural explanations. Regarding the anomalous acceleration of Three-Eyed Atlas, the astronomical community has proposed several mainstream hypotheses. We will rigorously examine each of these hypotheses and test whether they align with the complete observational data. First is the most widely cited natural explanation, the comet outgassing theory. Comets are composed of ice and dust. As they approach the sun, the icy crust absorbs heat and undergoes sublimation. Solid ice directly transforms into gas and erupts from the surface. These ejected gases act like miniature rocket engines, exerting a reaction force on the comet body that alters its velocity. This is known as a non-gravitational effect. A classic example is Halley's Comet, whose orbital period has changed due to outgassing effects. However, the thrust generated by cometary outgassing exhibits distinct characteristics. Eruptions typically occur on the sunlit hemisphere. Due to the irregular surface of the nucleus and the random distribution of vents, the net thrust direction is often complex and difficult to predict. Yet the thrust vector of Comet Atlas exhibits distinctly different properties. Its acceleration direction precisely aligns with its velocity vector. This is entirely consistent with directed propulsion aimed at increasing velocity. A random natural outgassing process is highly unlikely to produce such precisely aligned thrust directions. This constitutes the first major challenge to the simple outgassing hypothesis. Next, we examine observational evidence supporting or refuting this hypothesis. If such immense thrust originates from gas ejection, we should observe corresponding material release. According to rocket equation principles, generating the observed velocity increment requires ejecting a mass equivalent to the thrust. Calculating at typical comet gas ejection speeds of 500 meters per second to achieve a 300 meters per second velocity increment, Comet 3H BOP would need to eject 60% of its total mass. This figure is catastrophic and impossible. If such massive mass ejection occurred, the object's brightness, morphology, and orbit would undergo drastic changes. Yet we possess continuous monitoring data from the Hubble Space Telescope. Its high-resolution imaging spectrograph detected no significant expansion of the coma. Spectral analysis indicates gas production remains at moderate levels, consistent with solar heating expectations, yet far below the scale required to generate massive thrust. In other words, the object remains visually quiescent while exhibiting intense dynamic activity. This presents an irreconcilable contradiction. An alternative hypothesis posits trapped internal volatiles as the culprit. This theory posits the existence of high-pressure gas pockets within the object. Solar heat causes internal pressure to reach a critical point, ultimately rupturing the surface to form directed jets. This mechanism could theoretically generate powerful instantaneous thrust, but observational data similarly fails to support this hypothesis. First, such violent eruptions would create localized hotspots that our infrared detection equipment should easily capture. Yet no corresponding thermal anomaly signals appear in the infrared data. Second, a single eruption cannot explain the smooth acceleration lasting 30 hours. More critically, such explosive releases are destructive. We should observe new impact craters or geological changes on the surface. Subsequent image comparisons show no significant alterations in surface morphology. Let us consider the rotation-induced jet theory. This hypothesis posits that the object's rotation periodically aligns a fixed vent toward the Sun, resulting in periodic alignment with the velocity vector. However, we know Atlas's rotation period spans 117 hours, while the observed acceleration lasted only 30 hours, covering less than a quarter of a rotation cycle. Any rotation-related thrust should exhibit pronounced periodic fluctuations, yet the measured acceleration curve remains unusually smooth and continuous, showing no signs of oscillations synchronized with the rotation period. This renders the rotational jet hypothesis untenable in light of the data. Finally, we examine the shape effect hypothesis. Perhaps the object possesses an exceptionally unique geometric configuration, such as a sail-like asymmetrical shape, where solar pressure or rarefied gas exerts unbalanced forces on its surface, generating net thrust in specific directions. Computer modeling indicates that achieving the observed thrust magnitude and direction requires near-perfect asymmetry, akin to an engineered design which is extremely rare in naturally formed celestial bodies. Even if such an extreme shape existed, the thrust direction would constantly change with the object's rotation, unable to maintain a stable propulsion direction throughout the acceleration window. Yet the three-eyed Atlas achieved precisely this. After a systematic review of all mainstream natural hypotheses, we find each faces a dilemma conflicting with key observational data, whether it concerns the directionality of thrust, the smoothness of duration, the absence of ejected material scale, or the void in thermal signatures. All point to the same conclusion. Conventional natural mechanisms cannot fully account for this event. When all ordinary explanations are ruled out by evidence, we must turn our gaze toward more extraordinary possibilities. In the next section, we will explore the simplest inference. Could an artificial object equipped with a propulsion system explain all the mysteries? When all conventional natural explanations are systematically disproven by evidence, the logic of scientific inquiry guides us toward more extraordinary possibilities. We adhere to Occam's razor. Among competing hypotheses, the theory explaining the most observed facts with the fewest assumptions is typically the most preferable. Currently, only an intelligently designed artificial propulsion system can seamlessly account for all anomalous features of the three-eyed Atlas. Let us begin with the core issue of propulsion efficiency. The fundamental principle of rocket propulsion is the conservation of momentum, gaining forward thrust by expelling mass rearward. The key efficiency metric is specific impulse, which measures the engine's exhaust velocity. Chemical rockets achieve exhaust velocities around 3 kilometers per second. If the three-eyed Atlas gained thrust through natural outgassing, its exhaust velocity would be merely 0.5 kilometers per second. An extremely inefficient rate. This efficiency is extremely low. This is precisely why it requires ejecting absurdly disproportionate mass. But what if it employs advanced propulsion technology? For instance, ion thrusters can achieve exhaust velocities of tens of kilometers per second. Even more advanced fusion propulsion could be higher. By back-calculating using the rocket equation with a highly efficient propulsion system, it would only need to consume a negligible fraction of its total mass, perhaps less than 1%, to achieve the velocity increment we observed. This perfectly explains why we haven't detected massive cometary outbursts. Their mass ejection rates fall far below our detection thresholds. Propulsion systems eject matter in an orderly stream at extreme velocities, unlike comets' chaotic eruptions of dust and gas. Next, we analyze thrust directionality and control precision. Naturally occurring thrust vectors are random and divergent, while the three-eyed atlas maintains astonishingly precise alignment with its velocity direction. This requires a complete navigation and control system, including sensors to perceive its own attitude and flight path, along with actuators capable of precisely adjusting thrust direction. This capability is a hallmark of artificial spacecraft. From satellites orbiting Earth to probes journeying to outer planets, all rely on such systems for orbital maintenance and maneuvers. The timing of acceleration further reinforces this inference. The maneuver occurred within a 2-hour golden window after perihelion, the moment of peak orbital energy. Applying thrust here maximizes orbital modification efficiency. A natural process cannot actively select such precise timing, while an intelligent system would pre-calculate and await this optimal moment. This demonstrates clear intent and strategic planning, mirroring the decision logic we employ in deep space exploration missions. The strategic purpose of this maneuver also warrants deeper examination. The acceleration direction increases velocity rather than decelerating, which initially seems counterintuitive. If the goal is to remain within the solar system, deceleration would be expected. Yet, orbital mechanics are complex and intricate. By accelerating at perihelion, it actually elevates the aphelion of the orbit, altering the trajectory for exiting the solar system to enable a closer approach to Mars. This is likely the first step in a multi-stage orbital insertion maneuver. The next step may involve deceleration during a Mars flyby, combined with Mars's gravitational assist, ultimately achieving the goal of being captured by the solar system. This method of orbit alteration, leveraging the slingshot effect with minimal propellant expenditure, is precisely the strategy humans employ in deep space missions to conserve fuel. Finally, we must examine the acceleration profile curve. Observations indicate the acceleration process lasted approximately 30 hours, with both its initial peak and decay exhibiting unusually smooth gradients. A natural outgassing process would exhibit violent fluctuations due to surface sunlight variations and internal structural inhomogeneities. Yet the acceleration curve of the three-eyed atlas resembles throttle control in our engines, demonstrating a controlled, stable thrust output. In summary, an artificial object possessing an advanced propulsion system could simultaneously explain all critical anomalies: directional thrust, extremely low mass expenditure, precise timing, a smooth acceleration curve, and its strategic orbital modification effects. These characteristics collectively form a compelling inference. What we are observing may not be a lifeless interstellar rock, but a spacecraft constructed and operated by intelligent beings.